Hello students, this is Mr. Ezra. Today we're going to finish up section 5A.1, so this is part 2, and we're going to continue to talk about solving simple, easy logarithmic and exponential equations. So in the last video we began to discuss how to solve some of those, and we're just going to kind of pick up where we left off. I'll talk about several different examples along the way and how to handle those examples. So first up, we have log base 3 of x minus 2 equals log base 3 of 3x minus 6. What I want you to notice here is that the base of the log is the same on both sides of the equal sign, that there's nothing on the left side or the right side other than the log. And since that is the case, what is inside of the log on the left must be equal to what is inside the log on the right. This hopefully makes sense to you that everything else being equal, the insides must be equal too. So we're just going to come down and say x minus 2 must be equal to 3x minus 6. This becomes a real simple equation to solve. Now we're going to collect our variables to one side. So I'm going to subtract x to the right to get 2x minus 6 on the right, because 3x minus x is 2x. And then negative 2 is still on the left. And I'll collect my constant to the right by adding 6. To the left. I'll add 6 to the left to get positive 4 equals 2x. And then I'll divide both sides by 2. 4 divided by 2 is 2, and 2x divided by 2 leaves me with just x. So I get my solution. I will go ahead and say it probably won't happen at this point, but eventually logarithmic equations produce what are called extraneous solutions. They are things that are not possible. Algebraically, you get an answer, but when you plug it back in, it does not work. This one works. 2 minus 2 is 0. 3 times 2 minus 6 is also 0. Log base 3 of 0 is equal to log base 3 of 0. So we have no problems here. In our second example, we have the same situation where we have log base 7 on both sides of the equal sign. There's nothing else there, so we're going to take the insides of those logarithms and we're going to set them equal to one another. So x squared minus 5x is equal to 14. I see an x squared, my brain thinks quadratic. I've got to solve this quadratic. There are several ways that we've discussed for solving quadratics. I'm hoping that this one factors. So in order to see if it factors, I'm going to subtract 14 to the left side of the equal sign so that I have everything together on that side of the equal sign, and I'll start thinking about the things that multiply to give me negative 14 but add to give me negative 5, and I'm thinking maybe negative 7 and positive 2, because negative 7 times positive 2 is negative 14, and if I add the inside product and outside product together I get negative 5. So I've got the two factors, which would give me the two solutions of positive 7 and negative 2. So we can circle both of those solutions. They both work. Our next example, this one is a little different, isn't it? I do not have a log on both sides of the equal sign, so I can't just set the insides equal to one another. So what I want to do here is what we call isolating the logarithm. I want the logarithm, which is this whole thing right here, by itself on one side of the equal sign. So how can I get rid of this 3 that's in front of the log? Well, whenever you see a number touching something algebraic, it indicates multiplication. This is 3 times the log base 4 of x plus 2. To get rid of the 3, what we're going to do is we're going to divide both sides of the equal sign by 3. And that's going to allow us to cancel out that 3 on the left and just leave the logarithm behind. Log base 4 of x plus 2, and 6 divided by 3 is positive 2. At this point, I'm kind of stuck. So when you get a log on one side of the equal sign, first you isolate the log. Second, we're going to write it as an exponent. When we write it as an exponent, we get 4 to the second power. Remember the swoop method, right? Base of your log is the base of your exponent. You raise it to the other side, so 4 to the second power equals everything inside the log, this whole thing inside the log, x plus 2. So 4 to the second power equals x plus 2. At this point, now that I've written it as an exponent, I've got a pretty simple equation to solve. 4 squared is 16. And then in order to get rid of this plus 2, I'm going to subtract 2 on both sides of the equal sign to get 14 equals x. And that is going to be my solution. And you can plug it back in. It works. We're good to go. All right. Moving on from logarithms to exponents. Very similar idea here. When our base is the same on both sides of the equal sign and we have nothing else but the exponent and with the two exponents with the same base, we can take those exponents and set them equal to 0 because they must be equal to one another. So 2x minus 5 must be equal to x plus 3. I'm going to solve this simple equation. I'll subtract x to the left. 2x minus x is 1x. You know, I'm not showing my work here because we're kind of getting past that, but all I'm doing is collecting variables by canceling out this x on the right by subtracting it and moving it to the left by subtraction. I'll use the addition property of equality to get rid of the minus 5 on the left side, and that leaves me with x equals 8. And again, 8. Plug in at 8 for x here and here. Make sure that it works. Make sure you got the right thing, and we should be good. All right. We'll first back up. Notice that the base is the same on both sides of the equal sign. So we just set the exponents equal to one another, right? The bases are not the same here. And in fact, we have more than an exponent. So these kind of problems are similar to logarithms where you only have one logarithm. You have to isolate the exponent. When you don't have it on both sides, you've got to isolate the exponent. So again, 4 parentheses 3 to the x is 4 times 3 to the x. To undo that multiplication, I use the division property of equality. We use the division property of equality. We divide both sides of the equal sign by 5. That leaves us with 3 raised to the x on the left. And a 405 divided by 5 is, let's see, 81. 81. Now you might be able to do this in your head. We're asking ourselves 3 to what power is 81? So I guess the second step here is just to solve, right? Figure out what is true for x. Well, maybe I have to think about this. So 3 times 3 is 9. 9 times 3 is 27. 27 times 3 is 81. So this is going to be 3 raised to the 4th power. X has to be 4. All right, again, we have the exponent only one side of the equal sign, not on both. So we need to isolate this exponent. To do this, we're going to subtract 8 on both sides, and that's going to give us our base and exponent alone on the left side of the equal sign. 133 minus 8 is 125. Now at this point, because of the exponent x minus 4, I'm having a little bit of trouble thinking 5 to what power. Instead, I'm going to do something new. Okay, and what I'm going to do is I'm going to change the bases so that they're the same. I notice that 5 to the x minus 4 has a base of 5, and I think, well, I bet I could change 125 to have a base of 5 as well. 5 to what power is 125? So I start multiplying 5s in my calculator or in my head. 5 times 5 is 25. 25 times 5 is 125. So that's 5 to the 3rd power. Now that I have two bases that are the same, like we did a minute ago, I can take the exponent, x minus 4, and set it equal to the exponent 3 to solve my equation. I'm going to add 4 to both sides to get 7. Now it should work that when I do 7 minus 3, that's 5 to the 3rd power. 125 plus 8 happens to be 133. So when I plug it back in for x and do the math, it actually works. That's great. So we have another problem where it looks like we only have one exponent. But I look at this 8 and this 2, and in my brain I realize that I can change 8 to have a base of 2. So I'm going to leave the left to be 2 to the 3x. And I'm going to rewrite 1/8 to be 2 to some power. Now we have to remember a few things here. Number one, anytime our goal is to have a power that gives us a fraction like 1/8, we're going to have to use a negative exponent. And after we realize that, the question is 2 to what power is 8? 2 times 2 is 4, 4 times 2 is 8, so 2 to the third power. Since 2 to the third power is 8, 2 to the negative third power is 1 over 8. You've got to remember that. Now that our bases are the same, we can just focus on these exponents and set them equal to one another and solve. 3x equals -3, divide both sides by 3, I get -1. Plug it in, make sure that you get it right, check your answer, you never have to miss these. Or another example, this time I have exponents on both sides of the equal sign, but the bases aren't the same, so I can't just use that trick where I set the exponents equal, but can you re-express 16 to be a base of 4? And the answer is yes, you can. Sí se puede. Yes, we can. So how do we do it? We think 4 to what power is 16? Well, 4 to the second power is 16. Now, when you change this to be 4 to the second power, you still are raising that to this x minus 3. And the way that you handle that is you put parentheses and say that the new exponent is 2 times x minus 3. Now my bases are the same. I can take these exponents and set them equal to each other and solve. So I've got 4x plus 3 equals 2 parentheses x minus 3. First step that you want to do, I think, is to distribute the 2 into the parentheses on the right. That leaves us with 2x minus 6 when you multiply 2 into x minus 3. We're going to collect our variable terms to one side, so I'm going to subtract 2x to the left. 4x minus 2x is 2x. And then I'm going to collect my constants to the right, so I'm going to subtract 3 to the right to leave me with 2x on the left equals -9, because -6 minus 3 is -9. And then I'll divide both sides by 2 to get -9 over 2. That should be the solution, assuming that we've done all of our calculations correctly here. I think this might be the last one. Let's give it a go and see how we do. As always, when you are starting to feel comfortable, stop the video, try it on your own, see if you can get it right. I can't change to a common base of 25 here because 25 to the second power is much bigger than 125. So what I have to do is think of something that would be a base of both 25 and 125, and that number is 5. 5 squared is 25. Remember, whatever exponent is there, you put in parentheses, and it's going to become that 2 times 2x plus 1. So 5 squared gives us a 2 exponent. We're going to multiply by what's already there. On the right side, remember that in order to get a fraction, we need a negative exponent. And then we think 5 to what power is 125? And that happens to be 5 to the third power is 125. So 5 to the -3. Remember, there's already an exponent there. You put it in parentheses. Now you're good to go. Now we have base the same as base. We can take those exponents and set them equal to each other. 2 times 2x plus 1 equals -3 times 2x. I'll distribute on both sides of the equal sign to get 4x plus 4x plus 2 equals -6x. So I'm just multiplying 2 into the parentheses on the left and -3 into the parentheses on the right. In this case, I'm going to collect my variables to the right. So I'm going to subtract 4x on both sides to get 2 equals -10x. And then I'm going to divide both sides by -10 to get 2 divided by -10. X equals 2 divided by -10. Now, this isn't a good way to write our answer, is it? We want to simplify it. First, we never leave a negative in the denominator, so that negative is just going to come out front or put it in the numerator. Think of it this way: a positive divided by a negative is a negative. and 2/10 reduces to be 1/5. So 1/5 should be the value for x that makes this a true statement. Well, that is it for today. We've gotten through lots of examples in about 15 minutes. Hopefully it's starting to make sense, but as always, when you begin practicing in class, if you run into a problem, let me know. I'll be glad to help you out.